So let's have this one. This third component is natural transformations. Now, let me introduce this first as a separate component. But later we will show that this is not. This is actually some kind of a functor.
Yeah.
Okay? But let's, because doing that will give us two sides, and also doing it in this way also gives you another picture. So suppose we have two categories. Say the category A and a category B. And I have a functor f. So what is it doing if I have a diagram like this? Okay, so this is the composite. There are several other such diagrams.
Yeah.
This is going to be mapped by f to some other thing like this. Say, let's give some names. So this is my FA, this is my FB, and this is my FC. And if this is FG, this is G composed F, so this is FG, FF, and FGF. Suppose we have another functor also. So this will also map this into another diagram, similar diagram, right? So let me just copy this somewhere here. So and so these will be my G's. There can be several functors, but the real interesting part would be in trying to see if one can transform from the functor f to the functor g. Okay? From the functor f to the functor g. So if I am saying if I can transform, so definitely I would like a map like this, right? So it should come for each object. For each such object there must be morphisms in B from FA to GA, say alpha A, in B, and so on, right? But the whole point is much more than that. If it has to really transform, then it also must, in some sense, preserve this change from A to B.
Yeah.
This is the change from FA to GA. But A's are also changing to B, and FB's are also changing to GB's.
Yeah.
So if it has to be something nice, then the change from A to B, which is done by F, should also be respected. That means this part of the square must commute. That means I am saying the change from FA to say FB by f of f, GA to G of B, by G of F, these changes must be preserved by the changes from F to G. Okay?
Yeah.
So these must commute. Okay?
Yeah.
And that's exactly what a natural transformation is. And that's why we say it's naturally transforming. It's transforming from F to G, and natural in the argument A. Okay? Because if A is also get transformed, then the transformation is in line, is in keeping with the transformation there.
When you say natural in the component
Yeah.
A,
Yes, in the component.
what you say about B? Are you saying natural in component A because it originates from A?
No. I'm saying natural. Whenever there is a morphism
From A.
from in the category A,
Okay.
this diagram commutes. So whenever there is a morphism, the domain in the firstly the domains FAs are changing to GB in GAs.
Yeah.
That's fine.
Yeah.
But it's not arbitrary. Whenever the domain A is also changing to B,
Yeah.
all right, the change from FA to GA, that's also happening from FB to GB. But this change must be coherently with the change from A to B by F, whatever be that morphism.
Yeah.
Okay? So that's what I'm trying to say.
But when they say, it is natural in the argument.
A.
But what A as in a category?
Category.
Or
Yes. No. A as
A
this
as an
object.
object.
Yes.
Yeah.
So we often
But-
say this change. So alpha is natural in A. This is also how we will say it. Okay? Or alpha is a natural transformation from F to G. This is also another way in which we say. From the functor F to the functor G. Okay? Because functor A's are, this is where this functor is coming into the picture.
So in this case, the naturality is based on the original, on the domain of the R always initiated from A.
There are two components, right?
Yeah.
Which ones are those?
There are two components. Firstly, the functor values.
Yeah.
The functor values,
Yeah.
the FAs,
Mm.
they are changing to GAs.
Yeah.
But that could be quite wide. You give me, think B2B sets.
Mm.
You have two functors going into sets. I can define arbitrary, in any arbitrary way, a function from FA to GA for each A. But in defining any such function is not going to work.
Yeah.
I'm demanding a little more. What is it that I'm demanding? So just giving a family of, so let me start writing. You will see. So what is a natural transformation? A family of morphisms of B indexed by A naught. That means the objects.
Mm.
Okay?
Uh-huh.
Now the whole point is, just by giving a family of such morphisms is not enough.
Mm.
If it has to be natural, I have to also see that these objects A inside the category A itself are also getting transformed to some B, to some C, whatever. Here it's going to some C. Okay? So these are also getting transformed. Now, if the transformation, or if that family alpha A's do not respect the transformations internally that is happening within A, within the category A, then
It's not natural.
It's not natural, it's not good. So what is the goodness? The goodness part of it is whenever this A is getting transformed to B via some morphism F, then you have the corresponding morphism F of F from the functor. So this square must also commute. That means alpha B, you can go from FA to GB in two ways. First, you either go via the morphism part of F, functor F, and the change small f, and go to FB and use the change from FB to GB by alpha, or you could first change from FA to GA by alpha and then follow the path of GF. Both these two must be same. So that means these two diagrams must come. So that's the naturality, that's the maintaining. So the change from FA to GA is actually preserving the change of the arguments from A to B. Right? So in that sense, I am saying it is natural. A family of this such that whenever, so if is a morphism of A, then GF composed alpha A is alpha B composed FF. Right? That is this diagram. Okay? So this is a natural transformation. So this is a natural transformation. From A to B, from F to G. 1 minute. And we shall write this as alpha from F to G. Even like this. Okay?
Yeah.
Clear?
Yeah, that's clear.
Okay. Let's first give some examples of a natural transformation. Then we look. Let's take the most classical one. Suppose V is a finite dimensional vector space, real vector space. Okay? And now V star is the dual space. You know what is it, right? Yes. So which is nothing else but Hom V to R. And you know, point-wise we add in scalar. Okay. So, and we know V star star is the second dual. Now, the point is, in algebra, firstly, we know, it's also a known fact, that dimension of V is same as dimension of V star, and hence it's same as dimension of V double star. Right?
Yeah.
That's well known.
Yeah.
But let's look into the isomorphism from V to V double star. So what do I do? Well, you take an element here, and you have to give a element set TA. Okay? So what is TA? TA is actually a functional on V star. So what does it do? It takes a linear functional and evaluates it at A. Right? This is it. Okay. So firstly, is this linear? Obviously, the way we define V star, it's linear. A to TA is, and why should, so what is T of A plus B? So we know, what is it? T of A plus B at F. This is F of A plus B, which is FA plus FB. So this is nothing else but TA of F plus TB of F. So which is TA plus TB in this linear functional evaluated at F. Right? And similarly, so you know the A to TA is actually a linear. So linear, this plus, you'll be able to show T times T lambda A of F is lambda times TA of F. Right? So this shows that these two will show that A to TA is linear. Okay?
Yeah.
Good. Now what's the kernel? So suppose, what's the kernel of tau? A belongs to kernel of tau if and only if TA is 0. That means 0 means the 0 functional. That means for all F in V star, TA of F is 0, which is the same thing as saying for all F in V star, F of A is 0. For every linear functional, F's value is 0. A must be 0 therefore. Okay. Well, the easiest way is take a basis of the vector space. This will give you a basis for the dual space and so on and so forth, right? Okay. But from here you immediately conclude that A is 0. So tau is 1 to 1. Okay? And it takes a little more to say that tau is also. Now use a basis of V to show the what do I say? The equality of dimensions, I mean to say. So that means if A1, A2, An is in the basis, you show TA1, TA2, Tan, they are linearly independent, and they make a basis. Yes?
Okay.
So that's what shows that bases are same. So tau is 1 to 1 having the same basis, so it's an isomorphism. But something more than this. So what did I do? Observe. Let me now put a little more tau V. Okay? So I'm saying tau V. So what did I do? For each vector space, I have given you a linear map. This is a vector space. Okay? So I can see from finite dimensional vector spaces, two vector spaces there are two functors. One is the identity functor. Let me write it as this. And the other is the double dual functor. So this is from identity of here to double dual. Okay? I have given you a family of morphisms of finite dimensional vector spaces. It is much more, it is an isomorphism. But I have given you a morphism. Now suppose you have a linear transformation. Okay? What is this? So what is this? So if I have a linear transformation, this immediately gives me an F star from W star to V star. Why? Because you have given me this. It's just composition.
Yeah.
You give me a linear transformation and you compose. So this obviously gives me, so what is F star? F star, what is F double star? This takes a theta composed F star. Okay? Now, what I am trying to say is that this diagram commutes. Let's see. I take an A over here. I go to TA. Yeah? I take it to FA over here. And this goes to tau. Again I am saying T of FA. And this is F star star. So this is a member. This is like your theta, right? So this is TA composed F star. Okay? This, recall here is it. TA is a member of V double star, so it's like theta. F double star is this one. See what I am doing. This is tau V, this is F star star, F, and this is tau W. See, taking star means composing on the right by theta. So it's composing on the right by F star. Yeah? So I have to show this. Now how do I show this? Let me take a theta, a linear transformation from W to R. Let's see what does T of FA does. What is it? What am I doing? Let me take what is TA composed F star on theta. So this is TA of F star of theta. Right? This is TA of theta composed F. Right? That's my. Now TA, what is TA? TA is in V star star. Theta composed F is in V star. Right? Remember how was TA defined? It was the evaluation at F. So it is theta composed F at A. So it is theta at FA. Right?
Mm-hmm.
But then evaluation, so this is nothing else but TFA of theta. Yes? So you see, these two are same. So this diagram commutes. Okay? But now see what I am saying. What did I say? Okay, I gave, firstly this reverses the direction. Still fine. Still fine. But let us see, so this tau v's, these tau v's do not, it actually preserves the change in v.
Okay.
Right? So tau v's, we can say therefore that the tau v's preserve the change of v's. Okay? That means what I am saying is this tau v is a natural transformation from v to v double star. So going from v to v double star, we are doing it naturally. But here is a much more stronger statement. There does not exist any natural transformation from V to V star. Why? Suppose it did. Suppose is natural. Okay? So then if I have something like this, this is going to V star by alpha V, this is going by alpha W, but this actually reverses, right? So this must commute. Okay? This should commute. So this commutes. Okay? All right. Take the zero linear transformation. Everything is taken to zero. So then everything over here will also be taken to zero. W star to V star is zero. Right? So what is this? If I take f to be the zero linear transformation, you start from here, you have x, it goes to 0 by f.
Okay.
This is a natural transformation. This is a linear transformation. So this has to go to 0. No other way. Well, this is also a linear transformation. There is no other way. This goes to 0. But if x was non-zero, I know, I should say natural transformation, let me say another thing, plus a bijection. Okay? That means alpha v is a no bijection from v to v star, which is natural. Okay? We know that this is a bijection, so at an isomorphism. Okay? So therefore, if x is not equal to 0, this cannot go to 0. Okay?
Yeah.
You don't have to take even a bijection, a 1-to-1 plus an injection. So kernel is trivial, right? Because if this is non-zero, this cannot go to 0. If this alpha v's are 1-to-1, x non-zero cannot go to 0, right?
Yeah.
So you see what you are saying, just by giving a family of transform, we know from V to V star there is a bijection in finite dimensional case.
Yeah.
Right? There is already a bijection. We know that. Yeah? But that bijection, whatever bijection you might give me, okay, which is an isomorphism of vector spaces, that is not natural. So what does it mean? It means, if you now go back to the theory of vector spaces, how do you construct that bijection from V to V star? It very much depends on the choice of your basis that you did take for V. The corresponding basis of V star depends on your choice of basis in V. If you change the basis, the bijection changes, and changes in a very, very bad way, which is said by this non-commutativity, right? Yeah. It changes in a very, very bad way. Okay? So, but what about the other one? Whatever basis you might take in V, the description of the basis in V star, or the description of the bijection from V to V double star, is independent of the choice of your basis. That's the magic. Because you showed me that this is natural. Tau V's are natural, right? Yeah. And we know that this tau V is a bijection, right? Okay. What does this naturality therefore tell me? It tells me that whatever basis you might take for V, okay? Whatever basis you might take for V, the description of tau V is independent of that. Why is it so? Suppose you take two bases, B and B prime over here. Then V, instead of W, you once take V with the basis B. That gives you an isomorphism over here. Once you take V itself with the basis B prime, and F to be the isomorphism, because you change the basis, there will still be an isomorphism, right? This commutativity then tells that tau V, so both sides will be tau V. Tau V, so you're going via tau V, change of basis on the double star because of the change of basis here. That is the same as you change of basis and tau V. So tau V actually respects that change of basis. So it commutes with that change of basis matrix. Yeah? So that means it is independent of, that description is independent of the choice of your basis. But here, even if you had one, it is not independent. It is very much dependent on the choice of. So now you see what's the magic of this naturality. Yeah? So however V is changed to W, going to V double star is respected. But going to V star, you have to be careful. Yeah? So that's the subtle change, and that's the subtlety put by naturality. Okay? When I am saying it is a family of morphisms, but this family of morphisms change naturally with the change of the arguments, that is what I mean. Yeah? So you get the punchline now. Yeah? Clear?
Yeah.
Okay. So let's see another example. There are several, but which one? Okay, we'll come across many while I go, instead of wasting my time over here. Very soon I'll be giving you the examples as I go along. So now let's see, what did I do? So Here are categories.
Yeah.
So if I take functors, you know I can compose the functors in a very natural way. Yeah? And I have the identity functors. So the identity functors I'm drawing in another color. Okay? And they automatically compose with these things. So this composition of functors is associative. That's very natural because how we did it, it was in terms of two components, right? And G compose the identity functor is this, which is identity functor of C compose G. Okay, so it seems there is a category here. Yeah? All right. Now let's see another one. You gave me a functor, alpha, natural transformation. You give me another natural transformation. Remember what was so alpha from K to G. What was it? It was KB to GB. Family of morphisms. Okay. And what was beta? It was G to L. So GB to LB. This was alpha B. This was beta B. Okay? And if you had if the B changed to say B prime by something like this, well, for this part you were sure, K of B prime. This diagram commuted because alpha is a natural transformation. Yes, this is alpha B prime. And again over here, because beta is a natural transformation, you have told me. So LB prime, this part of the diagram also commuted. So the outer square also commuted. So taking beta B composed alpha B. So taking this, this family now. So this gives me a natural transformation, which we shall write as beta alpha from K to L. Yeah? And the way this is defined, it is clear that this composition is associative. Right?
Yeah.
And, well, if I look at this, KB to KB, the identity of KB. Well, this obviously defines a natural transformation, which I might as well write as identity K. Right? That is a natural transformation. The commutativity is clear. Yeah? And this is the identity with respect to this composition. Right? Okay? So we have, in this case, a second category, right, coming up here. This is also a category.
What called that category? Vertical.
Yeah, correct. The most natural thing to say is the vertical one, right? This is the vertical,
Yeah.
right?
Mhm.
Vertical. And this is, so in fact, this composition is called to be vertical composition.
Okay.
Yeah? So you're right. So we see from what we have done, two categories here. One is this side, the horizontal one, right?
Yeah.
Where we have several categories and functors between them, composition of functors, identity functor. Good. I have objects, I have morphisms, way to transform, the composition is associative, everything is right.
So
What-
in that one, is that one we could call functor category?
Yes, we could. Yes, correct. So which one as the functor category? The functor category would be this vertical one, because these objects are all functors from B to C,
Okay.
right? So this would be naturally to be named as the functor category. Of functors from B to C, right? That's the vertical one. And this is the other side is the category whose objects are all categories. So the best possible name is category of all categories, right?
Yeah.
But remember how we defined a category. It was a six tuple,
Yeah.
right?
Yeah.
Where the components were sets.
And now the components will go out.
Now we have a little bit of a problem. We are saying, well, it was a six tuple, good, where the components were sets. So we should have a set of objects. Remember?
Yes,
A0 was a
yes,
set of objects.
Yeah.
A1 was a set of morphisms.
Yeah.
Okay, so let's take, so this side you said this is the category of all categories, and this is the functor category, right? Now let's take the category of all categories, that one in our picture. What is its set of objects? This will be the set of all categories. Okay? Now I have a problem. So this is a set again. A big set, and herein is the set of all categories. Remember what a category was? A0, A1, partial 0, partial 1, E and M. The six tuple. Yeah? Remember how, just recall, how was a six tuple defined? Recall. What is a pair? Well, this is this set. Okay? What is the triplet? Well, this is AB and then a C. Okay? And so on, right? That was the set theory. Now we are coming to set theory. Alright? So in particular, A and B, if A was a very big set, that means if it is a big set, now what is a big set? Do I have a set of all sets? No. Okay. Okay.
I just draw it.
Yeah. Okay.
Yeah.
So herein starts the problem. It's a basic set theoretic problem. It's a basic set theoretic problem. And you cannot put, there are two kinds of sets. One is a large set and one is a small set. Things which are not small is large. Okay? Everything is not on the same platform. And that's the whole problem starts off with that Russellian kind of paradox. Yes? So what our goal is to have, so the escape route is to make small sets. What is a small set? A set is small if there exists a B such that A belongs to B. If I can find a set B such that A is an element of B, then I say A is small. And it is not a small set or a large set. It's not a small set. What does it mean? It means there does not exist any set B such that A belongs to B. Okay? That means for every set, A doesn't belong to it. So you cannot have a container inside which you can put it. Examples, the set of all sets. The set of all ordinals. The set of all topological spaces. And so on. These are all large sets. You cannot put it inside another set. Okay? So, if my A0 was a large set,
but in this case, this small set is basically this type of sets which are defined in a certain universe, defined universe.
yes, they are small sets.
Yeah.
Because they belong to that universe. Yes.
So in other words, this one we don't.
So that means that category that I am saying, the set of objects, if it has to be put inside another big set, that set of objects must be a small set. Yeah?
Yeah.
That must be a small set.
Yeah.
That means this must be small. Okay? So in particular, herein comes the notion of a small category. What is it? Remember,
The objects are set.
no, the other way around.
So
Remember, I'm saying, remember, you had this triplet. And your Akshams said that A0 is sitting inside A1 via those identities.
Yeah.
Yeah.
A0 is sitting.
Right?
Mhm.
So
Yeah.
if this was the set of A1 and this your identities, this is exactly a
A0.
copy of A0. Right?
Yeah.
So if you make A1 small, A0 has to be small.
Mhm.
But if A0 is big, large, A1 has to be big.
Mhm.
Yeah.
No other way. But there can be cases when A0 is small and A1 is large.
Yeah.
You can still have a case like that. Well, why not? Think of the following. You know that if you take cardinal numbers, their multiplication of cardinals is associative. Right? So take a one object category whose morphisms are cardinal numbers. Right? That's a monoid. Okay? But then the zero, the one, singleton is the identity, right? Right? But then how many cardinals are there? There are, as it's not a small set, it's a large set.
Yeah.
So number of morphisms is large, A1 is large, but A0 is small, it's a singleton. So you can have categories in which the number of morphisms is huge, but the not too many objects. Okay? Not too many objects. Alright? So that there can be there. But how to define a small category? Therefore, the most obvious way is to say if it has only a small number of morphisms. So if that means A1 is a small set.
So it's a small category if the
If-
home sets are.
If not all home sets.
Yeah.
If the total number of morphisms is a small set. It forces therefore the home sets are small.
Okay.
Yeah? Because home sets are subsets of the set of all morphisms. Yeah? So if A1 is a small set, the set of all morphisms is a small set. Okay? So it's just a set theoretic problem, and over here this has to be a small category. And then only you can have a set which contains them. Yeah? The moment this becomes large, you cannot have a set which contains any one of them.
Mhm.
Yeah? So it is not the category of all categories, but the category of all small categories.
So it's not that cat.
Yes. That is denoted by that. Of all small categories, not all categories. So objects are small categories,
Morphisms
are functors. And the usual composition and identities. Okay? Now, about a functor category. So that's one side of the story. About a functor category, Well, I need not produce any restriction, because what will be my set? The set will be the set of all functors between A to B. They could be large, but I still have, because between even large sets I have a set of functions. It's a large set again, right? But I'm not trying to put that inside another thing. Okay? That was the issue. I'm not trying to put it inside another thing. Here I was trying to put all of them inside another big bag, which is the set of all its objects. There was the problem. But here I'm just considering it separately as a as a single entity, right? Yeah. So this is often denoted in this way. This is the category of functors from A to B, morphisms are natural transformations, composition is the vertical composite, as you said. Okay? And identities is the identity natural transformation. Okay? So that's one side of the story. But we will now restrict ourselves to another aspect of this. Okay? Ready? Okay. So remember, let me draw that diagram again. Okay, so we are interested in this part. So this is our functor category, right? So okay. All right, good. Now let me have another such, and that's where so there is another such functor category. Okay, and okay. Now my question is obviously, how do they interact? How do these two interact? That's the most natural thing to ask. Okay, let's see. Let's first look into this part of the picture from Kp and Gh. K to G I am via alpha, P to H by gamma. Let's see. Now, look, from P, K of B. Okay? Now, from KB, I can go to GB. by alpha b. That's a natural transformation. Yeah?
From KB.
I can go to GB.
Yes, by alpha.
Yeah, okay.
And then I map it by P. So,
To P.
yeah?
Mm-hmm.
But,
Yeah, yeah, KB. Yeah. Mm-hmm.
okay?
Yeah.
KB to GB is alpha B, right?
Mm-hmm.
And I take its image under P. It's P of KB to P of GB, P of alpha B. But I have a gamma from going from P to H. So gamma, I can go from P at GB to H at GB via gamma. Right?
Yeah, yeah.
But I can do the other side also. From P of KB, I can go to H of KB first by gamma of KB. Yeah? And then from KB to GB, I was going by alpha. I take this image under H. So by the naturality of gamma, this diagram will commute. So this commutes. Yeah, this diagram commutes. So gamma GB P alpha B, gamma GB P alpha B is same as H alpha B gamma KB. Yeah, that's true. Okay. So I define gamma star alpha B to be gamma GB composed P alpha B, which is same as H alpha B composed gamma KB. Okay, see what, so that's why I was trying to draw that. Gamma GB composed P alpha B. Yeah, you see this Z.
Yeah.
Okay, there is also another Z is equal to H alpha B. So you start from here. Okay, H alpha B composed gamma KB. See, there is a Z either this way or that way. Okay, so that's the way how to remember this. So I always remember the gamma GB P alpha B. Okay. So these methods of school days,
Yeah.
cross multiplication and so on, if you remember, right?
Yeah.
Those are very helpful over here. Yeah, very helpful in remembering these small formulas. Okay. So now, what did I do? Let's see. So this is this map. This is this map. Right? So what did I do? I gave you a family of morphisms from PK to HG. See what I did? From PK to HG. Yeah? PK to HG. It's a functor from B to D. Right? Okay. So, what did I give you? So therefore, is a family of morphisms. Of D indexed by the objects.
This is not quite clear.
Which one?
The
That
D.
D.
Ah,
Looks like an O something.
Yeah, something. Yeah.
indexed by the objects of B. Yeah?
Mm.
And observe, PK is a functor from B to D. So is HG.
PK
Is a functor from B to D.
to D.
Yeah.
Yeah.
So is HG.
Yeah.
Okay? So the question naturally is this a natural transformation? So what do I have to do? I have to do if, say, B to B prime.
That is in B.
Yes, in B. What do I have to show? I have to show that this diagram commutes.
K.
PK to HG of B. It is gamma star alpha of B to this is goes to PK of B prime, HG of B prime, gamma star alpha prime. This is HG of G, and this is PK. Right? You have to say it's show that this commutes. Well, let's try. So HG of HG of G composed gamma star alpha of B. Okay, so this is HG of G composed. Let's come back. It is gamma GB. It's H alpha B composed gamma KB. That's the most reasonable now. Okay? H alpha B composed gamma KB. Yeah? Why I did was this was here. H of GG composed alpha B composed gamma KB. Yeah? Now observe. What was alpha? Alpha was from K to G. So if you had from B to B prime, KG and GG, so this is alpha B prime and this is alpha B. Okay? So GG composed alpha B. Oh, let me take it here. Let me bring this here. Let me bring this here. So then GG composed alpha B, this is nothing else but H of alpha B prime composed KG composed gamma KB. Yeah? Right? So this is now H of alpha B prime composed HKG composed gamma KB.
Where is that in the diagram? You said that in the diagram?
Which one?
Yes, these last two statements.
This one.
Yeah, this, yeah.
This GG composed alpha B is equal to alpha B prime composed KG by the naturality of alpha.
G alpha B, that's it. N alpha B kg. Okay.
Yeah? So now I used H over here, then HKG composed gamma KB. Yeah? Okay. Now, see what am I to do? I am to show that this is equal to gamma star alpha B prime composed PKG. Right? So let's see where remember, so I must be having H alpha B prime gamma K B prime, something over here. Okay? Now let's see what is gamma doing. What is gamma doing? Gamma is from P to H. Okay. So let's see now. Gamma is from P to H. So PKB to H of KB is gamma KB. And then I know what is HKG. This is going to HKB prime. Okay? Similarly, you have PKB prime here. So this is gamma KB prime here. And this is PK of G. Right? So this diagram commutes. HKG, so this is H alpha B prime. This one, HKG, so this is composed gamma KB prime composed PKG. Yeah? But now observe, what is this? This is nothing else but similar to this. So this is gamma star alpha at B prime composed PKG. Yeah? So that shows that this is natural. Okay? So there are a few other proofs which I'll leave it to you, but I showed this because for you to get the feeling of how you go about these proofs, right? You have to use this naturality of these things again and again. Okay? All right. Now, so so this is a natural transformation. So gamma star alpha is a natural transformation from PK to H. We did not write this, I wrote this extra. Yeah? So what did I do? Given these components, I can have a kind of a composition here. Right? Good. I have that. So the next question is very natural. So I have over here gamma star alpha. And I have over here delta star beta. I can vertically, because see, these two under seemingly like composition, it is giving another functor category from B to D. Right? There's a third layer which we are not seeing, right? The composite. This, and then the composite is coming up as this third layer, right? Which is the functor category from B to D. Yeah? So, KP is a member of that. So, over there, as a functor category of B to D, there is this composition, therefore in that vertical category. On the other hand, I also have these composites. I also have the composite beta composed alpha, right? I have this beta composed alpha, and I also have gamma delta composed gamma. What am I doing? Right? And then that is from K to L, P to Q. So I have a horizontal composite again. Yes? So now it's a big question. What about this? Indeed, these two are same. So this is called the Gorfeins Interchange Law. Let me write it, and is left for you to prove.
Coordinate.
Yeah. So star distributes over composition. So this is the vertical composition, this is the horizontal composition, right? The horizontal composition distributes over the vertical composition.
So the star
Is the
vertical.
No, this circle is the vertical,
Oh, circle is the vertical composition.
and this is the horizontal one. So this is delta composed gamma star theta composed alpha. Okay, prove this. I leave it to you. Okay, it's again along the same lines. Okay. Now, what does this mean? Therefore, let's see. What's the meaning of this? Let's look into CAT, the category of all categories. They are small categories. In this case, this is also a small category. Why? What do I have to check? The morphisms, the total number of morphisms is a small category, right?
It's a small set.
Yes, it's a small set, right? So what do I know? I know that. So that means how many natural transformations are there between two functors? Let's see that. So suppose I have to check this, where yeah,
How many transformations are there between the two functors?
see, how do I check? Suppose I know I have a small category. Okay. Now, what's another way to look into a small category? If I have each home set to be small, okay. So what is home set? Morphisms from A to B. And if I only have a small number of objects, then there is only a, if the set of objects is a small set, okay, then the Cartesian product of two small sets is also a small set, right? So A naught cross A naught shall also be a small set. All right. Now, then what is the home set? Home set is determined by two objects, right? So that means it AB pairs, right? If I can see that all the home sets are small, okay, and there is only a small number of objects, a small set of objects, then the total number of morphisms is actually this union, right? Since, see, what I am trying to say is, let me do that first. Observe. For a category, I am saying another one, say X. Hom X1 is actually union of AB coming from x0 cross x0 and Hom AB. Right? Because obviously these are subsets of the all morphisms, so this union is a subset of this. And if you take any morphism, you have a domain and a codomain, so it belongs to one of these Hom sets. So this is exactly the union, right? So if each Hom is a small set and x0 is a small set, then x1 is small. Why? Because a small union of small sets has to be small. Yeah?
Union of small sets is small.
Yes?
Yeah.
So that's the whole argument. So what do I do? To show that a category is small, the first thing is let me see the set of objects. I see it's a small set. Now let me see it's each Hom. Each Hom
Is small.
whether it's small or not. Okay? So yeah, I see each Hom set is small, the object number of objects is small, so the category has to be small. Okay? So that is my strategy. Okay. So now let's come back. So B and A are small categories. So now, how many functors from A to B? Let's see. So to give a functor from A to B, so a functor is, if to give a functor, and if you give
Is that F1 or just F?
F1.
You are the first one. No,
No,
this one.
it's a F.
This is F, just F. I'm saying if you have to give me a functor,
That's going to be dotted line.
Yeah.
Okay.
to give me a functor, you have to give me a pair of functions.
Yeah.
One from the object part and the other from the image part, right? Satisfying some more conditions. So this set of all functors is actually a subset of this, right? So what is it? You give me a function from A0 to B0, a pair of functions from A0 to B0, and a pair of functions from A1 to B1. So which I am trying to say is this actually, right? Right? A subset of this. Because not every such pair will give me a functor, but some of them will, because there are more equations. Right? Remember, preservation of domain, preservation of codomain, preservation of identity, preservation of composition, then only you will have a functor, right? So this pair of functions will have to satisfy some more equations. So it's not exactly just giving a set of functors, a set of functions.
Yeah.
So, but I can say this is always a subset of this. Okay? So this subset is nothing else but this. The set of functions from A0 to B0 and the set of cross A1 to B1. Right?
But this statement is not quite clear.
To give me a functor, you first have to give me a pair of functions, the object part and the image and the morphism part.
No, but to say this one is a subset of this, I don't understand why.
No. By this, when I put this bracket, I meant to say the set of all functors from A to B is a subset of the set of pairs of functions from A0 to B0 and A1 to B1.
Oh, okay.
Right?
Oh, yeah.
By putting that in those brackets, I meant the set. Okay.
You put the
Yeah.
brackets,
Correct. Let me put that. Yeah? Now it's clear, right?
Yeah.
But this, since B and A are small
But that one is a pair. No? Are you not looking at that one as a pair?
Yeah.
Yeah.
So then you can put the okay.
Yeah.
Or a set of pairs.
Right? Now, this, since B and A are small categories, A1, B1, A0, B0, all are small sets. So this is a small set, this is a small set. A product of small sets is a small set. So this is a small set. Right? So there is only a small set of functors from A to B when A and B are small categories. Okay? So, of the functor category A to B, B to the power A, the set of objects, which is the set of all functors from A to B, is a small set. Okay. So now let me look into Hom FG, where again I do a strange. So giving me a natural transformation, I'll have to give you a family. Satisfying some more conditions.
That is a family.
No. I'm saying giving a natural transformation is I have to give you a family satisfying some more conditions. So the set of all natural transformations is a subset of the set of all families, irrespective of whether they satisfy some conditions or not. Families of maps from like this. Right? Now what is this? Well, this is a member from Hom FB to GB. So this is, what is this? This is a member from Hom FB to GB and product of this. So what is the set I'm saying? It is indexed by B, so it will be a product over B, alpha B's, right? And what are alpha B's coming from? Alpha B's are coming from this, right? So this set is actually this set. Okay? Now, FB to GB, these are in B. B is a small category, so these are all sets. B naught, I'm sorry, not B naught, I should have been more careful. A naught, right? FB to G, FA, right? Sorry. A naught is also a small set, right? Remember, it has to be FB. F is defined on
A.
So A naught is also a small set. So a small product of small sets is obviously a small set. Yeah? So this is a small set. So each Hom set is a small set. Okay? So each Horn set is a small set, the set of all objects of this is a small set, so therefore by that token, so this is a small category. So if A and B are small categories, the functor category of all functors from A to B is still a small category. So what did I say? Therefore, A, B in cat implies is a small category. It's an object, right?
Are you saying cat sub 0?
So
cat zero, yeah,
the
objects of cat.
Cats, yeah.
Right? Okay. Now let's have a look into this whole thing that I was saying. This whole thing, this whole picture, whole scheme. Let's look into that. Okay. So that I have now shown is a small category. Good. So now let's see. Should I draw that picture again? Let's do that.
Look at this.
It'll cut it.
Yeah.
Okay. So now I'm done. Oh. Okay. Now the whole thing I wanted to say. Now observe. You take a functor from here, from C to D. Remember we spoke about the Cartesian product of two categories, right? And you take a functor from here and your composition produces a functor from here, right? So you take P and K, you take it to pk. Okay? And now everything is in small categories. So remember, all of this picture is actually embedded inside a bigger thing. Yeah? So these were categories. This horizontal side is a green side. Well, each one of these green things that I said, they were also categories and they are members of this again. Right? All right. So, and then if you take HG, this is going to HG. Here you take gamma alpha. This is going to gamma star alpha. Right? Suppose you take it a little further. QL, right? This goes to QL. This is delta beta. This goes to delta star beta. Okay? So this composite in the product is gamma composed delta. Del, the other way around. Delta composed gamma and beta composed alpha. So this should go, and this composite here is delta star beta composed gamma star alpha. So this should go to this equality is just saying that is Goldman's law, right? So this is saying composition is a functor.
Composition is a functor.
Is a functor. That's what it is saying. Okay? Composition is a functor. So in the category of small categories, composition then turns out to be a functor. So that is also, see, it's so rich. It is the category of small categories is becoming so rich now. In what ways? In what ways it is becoming rich? First, we can now start thinking as if these were some kind of zero cells, right? Then you had some kind of a morphism between these zero cells. Then you had so these were the one cells kind of. These were the two cells, right? It's again, there's a morphism again between them, yeah, which is making it into a category, right? So it's having more structure than we thought about it, right? Yeah, and it's getting much more interesting. It is a category, but it has much more structure than just a category, right? Between its morphisms, there is again another way, a morphism from a morphism to morphism, right? And they also make a category. So you can see, you can now imagine there is much more structure in this than just being a category. So would we be really wrong in saying as if this category is also enriched in categories? Enriched, because we can see that not only there are morphisms, so not only there are one cells between the zero cells, but between the one cells there is also another kind of, between them there is also another kind of a way to transform. And this way to transform is also making another category, right? So it is not only that, so it is the morphisms, the collection of morphisms between two objects is also making a category, right? So that's the extra thing that we are getting into the picture, in this picture, right? So it is, you can just assume, look into the category of sets. You have your nodes, the sets, you have your functions, right? You have your functions. But it is very difficult to think, it is very difficult, not sets, let's take topological spaces. You have your continuous functions. Or let's take your frames, your frame homomorphisms, right? But it is very difficult to think of a way of transforming from one frame homomorphism to another frame homomorphism such that this again makes another frame or another, yeah. But here we are having this transformation from one cell to another one cell, which if we might call them two cells, say this. So that's again one cells and two cells again make a category, another category. So there is category sitting inside category. So you see a kind of a meshed picture. Yeah. So as if so it's getting much more richer. Yeah. So we usually therefore call this a category enriched in categories. Okay.
Category enriched in categories.
Yeah. I'll give just one more example of this enrichment, and then I'll stop today. Okay. So, for instance, look into the category of abelian groups. Again, Okay? These are homomorphisms.
Homomorphisms group. Okay.
But then, if you look into this, Hom BC, this is again an abelian group.
Yeah.
Right? With the usual pointwise addition, yeah?
Mm.
So you see, it is not the picture is similar almost. It is not only the fact that we have abelian groups, so this as if this one cells, zero cells, okay?
Mm.
But these one cells also make another object of that same category, right?
Mm.
Which is the abelian groups, okay?
Yeah.
If you take k modules instead, if the picture was for k modules, where k is a ring, then this would not be a k module, but it would be an abelian group. So what I am trying to say is sometimes just from being a set, the morphism sets also come up with some extra structure,
Yeah.
right? And the composition becomes a structure preserving map, right? So if you look into this F and a G over here, and if you look into this map, which is taking Hom BC and taking you to Hom AD, yeah, this is also a group homomorphism, right? So the composition, not only do these objects, they become objects have a richer structure, but the composition becomes a morphism between such structures. Yes? So there is just not, it is just simply not well, take the case of topological spaces. You immediately do not have any such structure other than sets. Yeah? So we can say topological spaces, yes, it is also enriched, but just enriched in sets. But K modules or abelian groups, they are enriched in abelian groups. Yeah? The category of small categories is enriched, but enriched in categories again. Yeah?
Okay. Yeah.
Right? So you see, I am trying to give an idea of enrichment, which I will make formal much later.
Yeah.
But the enrichment we can try to see as just not being, these are just not being sets, but they have some more structure, and the composition is it turns out to be a morphism of that structure. Yeah? So it is a little more than just being a category. Yeah? So the category itself, you can then think that the category itself is coming now with some more kind of a structure in it. So we have to, when we deal with such, we have to be a little more careful than just about categories. Yeah? I'll stop here.
Okay.